Slit interference. Monochromatic light with wavelength lambda is incident on a screen with 3 narrow slits with separation d as shown in figure. So 3 narrow slits, separation d. Light from the middle slit reaches point P with electric field E cosine omega t. From the small angle approximation, light from the upper and lower slits reaches point P with electric fields E cosine omega t plus phi and E cosine omega t minus phi. So we have a symmetric situation here, respectively, where phi is 2 pi d sine theta over lambda is the phase lag and phase lead associated with different path lengths. Part A. Using either a phasor analysis or trigonometric identities, determine the electric field amplitude E sub p associated with the net field at point P in terms of phi. Part B. Determine the intensity I at point P in terms of the maximum net intensity I0 and the phase angle phi. Part C, there are 2 sets of relative maxima, one with intensity I0 when phi is equal to 2 pi m, where m is an integer, and another with a smaller intensity at other values of phi. What values of phi exhibit the lesser maxima? Part D, what is the intensity at the lesser maxima in terms of I0? Part E, what values of phi correspond to the dark fringes closest to the center? Part F, if the incident light has wavelength 650 nanometers, the slits are separated by 0.2 millimeters and the distance to the far screen is 1 meter. What is the distance from the central maximum to the first lesser maximum? Part G, what is the distance from the central maximum to the closest absolute maximum? Okay, so we have electric field components reaching point P with E cosine omega t plus phi and omega t minus phi phases. Now, using trigonometric analysis, we can calculate the total electric field at point P as the sum of the electric fields coming from the lower slit, upper slit, and the middle slit, cosine omega. So we have E0 cosine omega t minus phi plus E0 cosine omega t plus E0 cosine omega t plus phi. If we add them up, we can use the cosine A plus B expansion. So E0 cosine omega t minus phi is basically cosine omega t cosine phi plus sine omega t sine phi, and then we have E0 cosine omega t, and then we have cosine omega t plus phi, which is cosine omega t cosine phi minus sine omega t sine phi. You can see that we have 2 identical terms here, sine omega t sine phi and minus sine omega t sine phi. So they will cancel each other and we will be left with 2 cosine omega t cosine phi's and a cosine omega t here. So this will give us a total electric field E0 1 cosine omega t parentheses 1 plus 2 cosine phi. So cosine omega t cosine phi, cosine omega t cosine phi gives us in cosine omega t parentheses 2 cosine phi, and we have another cosine omega t here. This gives us 1 plus 2 cosine phi. Now, what is the magnitude of this oscillation? The magnitude of the electric field at point P will be 1 plus 2 cosine phi. So using trigonometric analysis, we have calculated the electric field amplitude at point P in terms of phi. So that's what we have done here. The alternative approach is to do phasor analysis. If we draw the electric field phasors here. We have E0 cosine omega t minus phi and then plus phi. So we have the minus phi, 0 phi equals 0 and plus phi. So we have the projections onto the y-axis here, basically giving us these electric field components. So what I have drawn here is the Phasor diagram. So the electric field magnitude at point P is basically simply E0 plus E0 cosine phi plus E0 cosine phi. So with that, we have E0 times 1 plus 2 cosine phi as the magnitude of the electric field vector using the phasor analysis. So drawing the electric field phasors at point P, we can add them up to get the total magnitude. So the magnitude of the electric field at point P is basically shown by the y-axis here. So we take the projections onto the y-axis for these phasors and we obtain the total electric field magnitude. Now part B asks us the intensity at point P in terms of the maximum intensity I0 and phase angle phi. Now we know that the intensity at any point is proportional to the magnitude of the electric field at that point squared. So the intensity is proportional to 1 plus 2 cosine phi squared. Or we can say that intensity is a constant A times 1 plus 2 cosine phi parentheses squared. So where do we get the maximum intensity? We will get the maximum intensity for phi is equal to 0 degrees. So basically cosine 0 gives us 1 here, 1 plus 2, 3 square. So this gives us an I max, maximum intensity, to be 9 times A. That's what I'm going to call I0. So what I see then is I is equal to I0, A, which is I0 divided by 9, 1 plus 2 cosine phi parentheses squared. So I have written the intensity in terms of the maximum intensity. So you can see that the maximum intensity corresponds to 9 times A, which is I0. So I0 divided by 9, 1 plus 2 cosine phi parentheses squared is the intensity at point P. So this is the intensity at point P. Now part C asks me about the lesser maxima. What values of phi exhibit the lesser maxima? So where do we get maximum intensity here? For maxima, we require, since it's an extremum point, the derivative of intensity with respect to phi to be equal to 0. So what is the derivative of intensity with respect to phi? It is 2I0 divided by 9, 1 plus 2 cosine phi, multiplied with the derivative of 1 plus 2 cosine phi, that is minus 2 sine phi, and this has to be equal to 0. And let's also do C and D together. Now sine phi equals to 0 gives us phi is equal to 0, pi, 2 pi, 3 pi, 4 pi, etc. Okay, so if we have phi is equal to 0, 2 pi, 4 pi, or 2m pi, as mentioned in the problem statement, what would be the intensity? We would have cosine 0 equals to 1 here, so we would have 1 plus 2, 3 squared 9, 9 divided by 9, we would obtain an intensity of I0 that is the actual maximum, primary maximum I0. So if we get rid of these ones, we will find that there are others, pi, 3 pi, 5 pi, etc. Those will correspond to the lesser maxima. So we will see lesser maxima occurring at phi is equal to pi, 3 pi, 5 pi, etc., which is 2m minus 1 pi. And what is the intensity in that case? When phi is equal to pi, we have minus 1 multiplied by 2. That gives us minus 2. 1 minus 2 is minus 1 squared, gives us 1 I0 over 9. So the secondary maxima will have an intensity I0 divided by 9. So this will be our lesser maxima. All right. And we see that the intensity for the lesser maxima is I0 divided by the number of slits squared, n squared, and that is I0 divided by 3 squared. And the number of secondary maxima is n minus 2. So we have 3 slits minus 2, that is 1 lesser maxima. Okay, so we have the number of secondary maxima equal to 1. So that's n minus 2. All right, so what about this becoming 0, 1 plus 2 cosine phi becoming 0? Well, in that case, we would have cosine phi equals to minus 1 over 2. When cosine phi is minus 1 over 2, you can see here we will obtain a 0. Intensity would be 0, so the other extremum point of cosine phi equals minus 1 over 2 corresponds to the minima. So in part C, we were asked to find the values of phi that exhibit the lesser maxima. Those are 2m minus 1 pi, where m is an integer. So m is 1, 2, etc. And then we have the intensity at the lesser maxima in terms of I0 in part D that we have found to be I0 over 9. If we substitute the phi values into the IP, we obtain I0 over 9. And also looking at 1 plus 2 cosine phi equals 0 gives us the minima. Now let's move on to part E. Part E is asking us what values of phi correspond to the dark fringes closest to the center. Well, as we have found out in the previous part, cosine phi equals minus 1 over 2 is the condition for the minima. And when does that occur? When phi is equal to plus or minus 120 degrees. So we have a cosine of 120 is equal to minus 1 over 2. So those are the minimum phi values near the center. Minimum phi values near the center. Now part F. The incident light has wavelength 650 nanometers, slit separation and distance to the screen is given. We want to know the distance from the central maximum to the first lesser maximum. Okay, so wavelength is 650 nanometers. Slit separation is 0.2 millimeters. And the length is 1 meters, distance to the screen. So if you see here, we have 3 slits, the distance is L, and we're trying to find the location of the basically the first lesser maximum with respect to the central maximum here on this viewing screen. Now the phase lag or phase lead divided by 2 pi is equal to path difference divided by lambda. So we have path difference is equal to lambda phi divided by 2 pi. And when do we obtain the first lesser maximum? When phi is equal to pi. Phi is equal to pi is the first lesser maximum. So we substitute pi here, lambda pi divided by 2 pi gives us lambda over 2. So path difference of lambda over 2, which makes perfect sense. So tangent theta, on the other hand, from this geometry here, you can see is y divided by L. So we have y divided by L, and the first lesser maximum or secondary maximum is at phi is equal to pi. The path difference d sine theta must be equal to lambda over 2. So you can see from our parallel ray approximation, we have a path difference of d sine theta. So now here, this is basically corresponding to 2d, not d. So we have a slit to slit separation here. This is equal to d. So 1d and 2d. All right. So with that, we obtain sine theta must be equal to lambda divided by 2d. That is 650 nanometers, 650 10 to minus 9, divided by slit to slit separation, 2 times 0.2 10 to minus 3 meters. And that gives us 0.001625. Now this is such a small sign, that means the angle is very small. Sine theta is approximately equal to tangent theta, approximately equal to theta because the angle is small. So we obtain the position y, tangent theta is y over L, y is equal to L times approximately theta times L. So 0.001625 times 1 meters. This gives us the approximate position of the first lesser maximum to be 1.63 millimeters with respect to the central primary maximum. Okay, now in part G, the distance from central maximum to the closest absolute maximum is asked. So let's see, where is the closest maximum? So we have phi equals 0, central maximum, 2 pi is the closest maximum. So we will have now phi is equal to 2 pi. The path difference, corresponding path difference will be one wavelength. So d sine theta is equal to lambda, which gives us sine theta is equal to lambda divided by the slit to slit separation d, which is basically 2 times 0.001625. So in the previous case we had lambda over 2d, now we have lambda over d, so it's twice the previous answer. So this is 0.00325, and once again this is a small angle, y is approximately equal to L times theta, 0.00325 meters. In other words, the position of the first absolute maximum is 3.25 millimeters distance from the central maximum. Okay, now if you look at the first lesser maximum, it's at 1.63 millimeters. First primary maximum is at 3.25 millimeters. If you divide 3.25 by 2, you would obtain something not equal to 1.63. So 1.63 multiplied by 2 will give us basically 3.26 millimeters or something. It's close, but it's not exactly in midway. So, but it's very close. So note that the first lesser maximum is approximately, because it's very close, is approximately midway between two absolute maxima. All right. So in this problem, we have talked about three-slit interference, looking at the rays coming from three different slits at point P. We have a path difference developing due to the phase difference developing due to the path differences. We have d sine theta plus d sine theta on one side and minus d sine theta on the other side, corresponding to plus phi and minus phi path differences for the rays reaching at point P. Now, using phasor analysis or trigonometric identities, we determine the total electric field. If we add up the electric field components, we see it's E0 cosine omega t 1 plus 2 cosine phi, which has a magnitude 1 plus 2 cosine phi. Using phasor analysis, if we plot the electric field phasors here, each making an angle, so they all have cosine omega t, but there's a phase difference. One is minus phi, one is plus phi. Their projections onto the electric field axis at point P, we see that the magnitude is 1 plus 2 cosine phi times E0. The intensity is proportional to amplitude squared, so it's 1 plus 2 cosine phi squared. So it's a constant multiplied by this. And for phi is equal to 0, we obtain the maximum intensity, which is 9A. So maximum intensity I0 is 9A. So that's this constant A is I0 over 9, 1 plus 2 cosine phi squared. The maxima will correspond to the derivative of di d phi becoming 0. So dip d phi is equal to 0. Which gives us both the locations of maxima and minima actually. So sine phi equals to 0 occurs at 0 pi, 2 pi, 3 pi, 4 pi. These are the maxima, and cosine phi equals minus 1 over 2 gives us 0 intensity here, which are the minima. So we substitute these values here, 0, 2 pi, 4 pi, 2n pi. What do we see? We obtain intensity of I0. If we substitute the other ones, pi, 3 pi, 5 pi, etc., we obtain I0 over 9. Because this is minus 1, we obtain 1 squared, which is I0, giving us I0 over 9. Secondary maxima have intensity I0 over 3 squared, I0 over n squared, and the number of secondary maxima is n minus 2, that is 1. 1 secondary maximum. So that just like we have suggested in the lecture. Now cosine phi equals minus 1 over 2 corresponds to minimum, which corresponds to a phase difference of 120 degrees. So the minimum phi values near the center. Okay. Now we have lambda is equal to 650 nanometers, d is 0.2 millimeters, L equals 1 meter, some numerical values here. What is the location of the first lesser maximum? That is, we're looking for phi equals pi, and that corresponds to a path difference of lambda over 2, d sine theta equals lambda over 2, and because the angle is small, tangent theta is y over L, is going to give us L times theta for y, so we can find the location here. For the phi equals 2 pi, delta equals lambda case, we obtain basically an angle that is almost twice of the previous one because of the small angle approximation, and y is equal to L theta gives us 3.25 millimeters. And because of the small angle approximation here, we have basically the first lesser maximum approximately midway between two absolute maxima. 0 and 3.25 divided by 2 gives us approximately 1.63 millimeters.